So now we have a classic physics demonstration where we take various different objects and we're going to roll them all down the exact same inclined plane. Now, the question is, which one will reach the bottom first? Well, they all have moments of inertia, and that moment of inertia will affect how fast they reach the bottom. So we know that the moment of inertia around the center of mass is equal to some constant times mr squared. For our hollow cylinder, the moment of inertia around the center of mass is just mr squared. For a solid cylinder, it's 1/2 mr squared. If it's a solid sphere, it's 2/5 mr squared. A hollow sphere would be 2/3 mr squared. And we want to see which one reaches the bottom first. And first, let's take a look at it just from an energy point of view. Then we'll talk about how we deal with Newton's second law problems where we include both forces and torques. But just looking from an energy point of view, we can learn quite a bit. First off, I know that at the beginning I have potential energy, but that my rotational kinetic and my translational kinetic are both 0. At the end, my potential energy is 0, assuming I set my 0 point right there, but I have both rotational and translational kinetic energy. So this is going to be mgh is equal to 1/2, rotational is I omega squared, and the kinetic is 1/2, or the translational is 1/2 mv squared. Alright, but I can put in this form right here, and so this is 1/2 beta m r squared omega squared plus 1/2 mv squared. And looking at this beta here, this m should be the same as that m. Beta just tells us what kind of an object it is. And r squared omega squared, we just learned r omega is the same as v center of mass. So what I get, I can first cancel out all the m's. And I get GH is equal to 1/2 beta plus 1, beta from here, 1 from there, v squared. So the bigger beta is, the smaller the velocity at the bottom is going to be. The smaller the velocity at the bottom is, the slower it's moving, and probably the slower it moved the entire way down. So what that tells us is that as the moment of inertia gets bigger, okay, I'm going to be slower at the bottom and therefore take a longer time to get down. The reason, when I have a larger moment of inertia, more of the energy has to go into rotation, leaving less of the energy available for translation that actually gets me down the ramp. So the ones with the highest betas, hollow cylinders for example, will get there latest. The ones with the lowest beta, solid cylinder, will get there first. There are other tricks you can play with it. For example, if you were to roll a soda can down, well, with a soda can, the outside part of the can is in fact a hollow cylinder, and you would expect it to go slow. In fact, an empty soda can will go very slow. However, the liquid inside the can being totally fluid, does not have to rotate at all. As a result, only a very small fraction of the mass rotates, and a soda can will slide down very quickly. It'll approach what you would get for an object sliding without resistance. Notice, and this sometimes surprises people, sliding without friction would give me mgh equals 1/2 mv squared. M cancels. Notice with no plus beta, I would actually get a much larger velocity sliding without friction than I do rolling down. Rolling always has some friction in it. Alright, so we can see just from an energy analysis that the one with the largest moment of inertia will be last, the one with the smallest moment of inertia will be first. Next, we want to talk about how we could actually figure out the acceleration from a Newton's second law involving both torques and forces analysis.